Long before the eruption of 1980, eruption of Mount St. Helens shocked the world with its lateral blast, collapsing summit, and ash cloud that drifted across North America. Another volcano hidden deep in the wilderness of the Cascade Range had already demonstrated that the region was capable of something far larger. It sits isolated among glaciers, forests, and rugged valleys in northern Washington state, quiet enough today that many people have never even heard its name. Yet beneath that silence lies one of the most explosive volcanic systems in North America. What happens when a volcano builds pressure for centuries beneath thick continental crust? What kind of eruption forms when gas-rich magma rises through ice-covered mountains and unstable volcanic rock? And how could a volcano that most people overlook produce eruptions estimated to be several times larger than one of the most infamous eruptions in modern American history? The answer is Glacier Peak, a remote stratovolcano buried within the wilderness of northern Washington. Despite its lower public profile compared with Mount Rainier, Mount Hood, or Mount St. Helens, Glacier Peak has a violent geological history that places it among the most dangerous volcanoes in the Cascade Arc. Geological evidence shows that during the mid-Holocene, Glacier Peak generated enormous explosive eruptions that released ash across large sections of western North America. Some eruptive phases are estimated to have been roughly 5 times larger than the 1980 eruption of Mount St. Helens in terms of erupted material volume. These events were not isolated explosions. They were the surface expression of deep tectonic and magmatic processes operating beneath the Pacific Northwest for millions of years. To understand why Glacier Peak is capable of such eruptions, it is necessary to go far below the volcano itself, descending into the tectonic engine that powers the entire Cascade volcanic chain. The Cascade Arc exists because of the ongoing subduction of the small but geologically powerful Juan de Fuca Plate beneath the North American Plate. Off the coast of the Pacific Northwest, dense oceanic lithosphere moves eastward and sinks into the mantle along the Cascadia subduction zone. As the slab descends to depths of roughly 60 to 100 miles, or approximately 100 to 160 kilometers, increasing pressure and temperature destabilize hydrous minerals trapped within the oceanic crust. Those minerals release water and other volatiles into the overlying mantle wedge. This process fundamentally changes the melting behavior of the mantle. Normally, mantle rock remains solid even at extremely high temperatures because of immense pressure. But the addition of water lowers the melting point of the surrounding peridotite. Partial melting begins within the mantle wedge, generating buoyant magma that rises toward the crust. This is the core mechanism behind arc volcanism throughout the Cascades. The magma generated beneath the Cascades is not uniform. As it ascends through thick continental crust, it evolves chemically through fractional crystallization, crustal assimilation, magma mixing, and volatile accumulation. Basaltic magma entering the crust may stall in magma reservoirs where minerals crystallize out over time. Dense minerals such as olivine, pyroxene, and amphibole settle or remain behind, enriching the remaining melt in silica. Simultaneously, ascending magma may melt or absorb portions of continental crust, further increasing silica content and volatile concentrations. This evolution matters enormously because silica-rich magma behaves very differently from low-silica basalt. Basaltic magma, like that seen in Hawaii, tends to flow relatively easily because of lower viscosity. But andesitic and dacitic magma, the dominant magma types associated with Glacier Peak, are far more viscous. Their internal molecular structure resists flow, trapping dissolved gases under pressure. As magma rises toward the surface, confining pressure decreases. Dissolved water vapor, carbon dioxide, sulfur dioxide, and other gases begin to exsolve, forming bubbles within the magma body. If the magma is too viscous for those gases to escape efficiently, pressure accumulates catastrophically. That pressure accumulation is one of the defining characteristics of Glacier Peak's eruptive history. The volcano is built primarily from andesite and dacite, indicating repeated cycles of evolved magma storage and explosive eruption. Unlike broad shield volcanoes constructed by fluid basaltic lava, Glacier Peak developed as a steep stratovolcano through alternating layers of lava flows, ash deposits, pumice, and pyroclastic material. Every explosive eruption added unstable volcanic sediment to the growing cone, while glaciers later carved and destabilized the mountain further. The location of Glacier Peak within the Cascades also contributes to its geological behavior. The volcano sits in an area of thick crust influenced by regional tectonic compression and faulting. Magma rising through this crust encounters multiple storage zones where it can reside for long periods. During storage, magma cools slowly, differentiates chemically, and accumulates volatiles. Over time, these reservoirs may become compositionally stratified, with more evolved magma occupying upper sections and hotter mafic magma intruding from below. That interaction between new magma injections and older evolved magma can be highly destabilizing. When hotter basaltic magma intrudes into cooler silica-rich reservoirs, thermal and chemical mixing may trigger rapid volatile exsolution. Crystals already present within the magma can become remobilized. Gas pressure rises dramatically. The reservoir may then fracture surrounding rock and initiate eruption pathways toward the surface. The geological record preserved around Glacier Peak indicates that this system repeatedly crossed the threshold into catastrophic explosive behavior during the Holocene epoch. Roughly 13,000 years ago, shortly after the retreat of major continental ice sheets from the Pacific Northwest, Glacier Peak entered one of its most active eruptive periods. Massive explosive eruptions dispersed ash across Washington, Idaho, Montana, Alberta, and beyond. Tephra layers identified in lake sediments, peat bogs, and soil sequences reveal that Glacier Peak was capable of generating sustained Plinian eruptions with eruption columns penetrating deep into the atmosphere. A Plinian eruption occurs when rapidly expanding volcanic gases fragment magma into fine ash and pumice particles that are blasted vertically into the atmosphere at extreme velocities. The eruption column behaves almost like a thermal engine. Hot fragmented material rises because of buoyancy and entrainment of surrounding air. If eruption rates remain high enough, columns can rise more than 12 miles or 20 kilometers above the volcano. At Glacier Peak, several eruptions likely produced columns approaching or exceeding these heights. As the eruption column rises, prevailing winds distribute ash over continental scales. Coarse pumice falls relatively near the volcano, while fine ash may travel hundreds or even thousands of miles. Geological mapping shows that Glacier Peak ash deposits spread across enormous areas of western North America. Some deposits are so widespread that they serve as important chronological markers for scientists reconstructing ancient environmental conditions. But the ash cloud itself represented only part of the danger. The most devastating processes likely occurred closer to the volcano in the form of pyroclastic density currents. These are ground-hugging avalanches of superheated gas, ash, pumice, and rock fragments moving at speeds that may exceed 100 miles per hour or more than 160 kilometers per hour. Pyroclastic flows form when eruption columns collapse under their own weight or when lava domes explosively disintegrate. At Glacier Peak, the combination of viscous magma and high volatile pressure created ideal conditions for dome growth and collapse. Dacitic magma tends to extrude slowly, piling near volcanic vents rather than flowing away easily. As domes grow, internal gas pressure and gravitational instability increase. Portions of the dome may collapse, decompressing gas-rich magma and triggering explosive fragmentation. The resulting pyroclastic flows sweep down valleys with extraordinary destructive power. The geological deposits surrounding Glacier Peak contain thick accumulations of pumice-rich pyroclastic material, indicating repeated generation of these currents. Some deposits traveled many miles from the volcano, filling valleys and reshaping drainage systems. The thermal energy involved would have been immense. Temperatures inside pyroclastic flows can exceed 1,000 degrees Fahrenheit, or approximately 540 degrees Celsius. Organic material caught in their path is carbonized instantly. Water bodies may flash into steam. Forests are flattened and buried beneath meters of ash and pumice. The explosive power of Glacier Peak becomes especially striking when compared with the 1980 Mount St. Helens eruption. That eruption released approximately 1 cubic kilometer, or about 0.24 cubic miles, of dense rock-equivalent material. Some of Glacier Peak's major Holocene eruptions are estimated to have released several cubic kilometers of material, potentially approaching 5 times that volume. This does not necessarily mean every eruptive process was identical in style or energy, but it does indicate that Glacier Peak's magma system was capable of sustaining much larger eruptive output. One major reason for this scale difference lies in magma storage duration and volatile concentration. Mount St. Helens in 1980 involved rapid decompression caused by a sector collapse that uncorked a pressurized magma system. Glacier Peak's larger eruptions may have involved longer-term accumulation of evolved magma within crustal reservoirs, allowing enormous volatile pressures to develop before catastrophic release. Another crucial factor is glaciation. Glacier Peak, as its name suggests, has long been heavily glaciated. During eruptive periods, interaction between magma and ice likely intensified explosive behavior. When magma encounters ice or meltwater, heat transfer occurs extremely rapidly. Water flashes into steam, expanding violently. This process, known as phreatomagmatic interaction, can fragment magma even more efficiently than magmatic gas expansion alone. Phreatomagmatic explosions generate very fine ash because thermal shock shatters magma into microscopic particles. They also increase eruption column buoyancy by injecting additional steam into the atmosphere. Around Glacier Peak, thick ice cover during portions of its eruptive history may have amplified fragmentation rates and accelerated lahar generation. Lahars are volcanic debris flows composed of water, ash, rock fragments, sediment, and organic material. They behave like fast-moving rivers of wet concrete. Glacier Peak is particularly capable of producing lahars because of its steep slopes, abundant loose volcanic sediment, and heavy snow and ice accumulation. During eruptions, pyroclastic flows and hot ash rapidly melt glaciers and snowpacks, generating sudden floods that mix with volcanic debris. Once initiated, lahars can travel astonishing distances along river valleys. Geological evidence indicates that Glacier Peak lahars move far downstream through the Skagit and Stillaguamish drainage systems. These flows buried floodplains, altered river channels, and deposited thick sediment layers over broad regions. Unlike lava flows, which often move slowly enough to avoid, lahars can arrive with little warning and maintain destructive momentum for many miles. The mechanics behind lahar mobility involve both water content and sediment concentration. High sediment loads increase flow density while still allowing fluid movement. Boulders the size of houses may be transported within the flow matrix because the mixture behaves as a non-Newtonian fluid. Internal turbulence and pore pressure reduce friction between particles, allowing massive debris volumes to move efficiently downslope. Glacier Peak's eruptive history also reveals important information about magma chamber architecture beneath Cascade volcanoes. Modern geophysical studies suggest that volcanic systems rarely contain enormous, fully molten magma chambers. Instead, they consist of crystal-rich mush zones with interconnected pockets of melt. Over time, injections of hotter magma can remobilize portions of this crystal framework, increasing melt connectivity and eruptibility. This concept changes how scientists interpret large explosive eruptions. Rather than imagining a giant underground lake of liquid magma waiting to explode, researchers increasingly view volcanic reservoirs as dynamic systems fluctuating between partially molten and eruptible states. At Glacier Peak, repeated magma recharge events may have progressively heated and mobilized crustal reservoirs until eruption thresholds were reached. Gas plays a central role throughout this process. Water dissolved within magma under high pressure remains relatively stable at depth. But as magma rises, decreasing pressure allows volatile exsolution. Tiny bubbles nuclein expand. If enough bubbles connect, permeability may develop, allowing gas escape. However, viscous magma often prevents efficient degassing. Pressure then rises internally until fragmentation occurs. Fragmentation is the transition point between magma behaving as a liquid and behaving as a particle suspension. Once gas volume exceeds a critical threshold, the magma shatters into ash and pumice fragments propelled by expanding gases. This process converts stored chemical and thermal energy into explosive kinetic energy. The pumice generated during Glacier Peak eruptions provides important clues about these mechanisms. Pumice forms when gas-rich magma decompresses so rapidly that bubbles become frozen within volcanic glass. The rock becomes extremely vesicular, often light enough to float on water. Microscopic examination of pumice textures allows volcanologists to reconstruct ascent rates, degassing behavior, and eruption dynamics. Some Glacier Peak pumice deposits show evidence of rapid ascent from deep crustal storage zones. Large bubble structures indicate volatile-rich magma undergoing catastrophic decompression. Crystal assemblages reveal complex thermal histories involving repeated magma injections and mixing events. Together, these observations paint a picture of a highly dynamic volcanic plumbing system operating beneath the Cascades. The regional tectonic environment further complicates this system. The Cascadia subduction zone is capable not only of generating arc volcanism, but also massive megathrust earthquakes. Stress changes associated with tectonic deformation may influence magma migration pathways over geological timescales. Fault systems within the crust can act as conduits for ascending magma or barriers that redirect flow laterally. In addition, crustal thickness beneath the North Cascades influences magma evolution. Thick crust provides more opportunity for magma differentiation and assimilation. As magma stalls repeatedly during ascent, silica content and volatile concentrations increase, enhancing explosive potential. This is one reason Cascade volcanoes frequently produce andesitic and dacitic eruptions rather than purely basaltic activity. Glacier Peak's remote location also masks its true scale. Unlike more symmetrical and visually dominant Cascade volcanoes, Glacier Peak is partially hidden by surrounding rugged terrain. Yet geologically, it has been one of the most productive explosive centers in the arc during the Holocene. The volcano's edifice has been deeply modified by glaciation, erosion, landslides, and previous eruptive destruction, obscuring evidence of older eruptive stages. Volcanic edifices are inherently unstable structures. They are built rapidly from fragmented material, hydrothermally altered rock, and steep lava accumulations. Hydrothermal fluids circulating through volcanic systems chemically weaken rock by converting strong minerals into clay-rich assemblages. Over time, this alteration reduces slope stability and increases collapse potential. At Glacier Peak, extensive hydrothermal alteration combined with glacial erosion likely contributed to sector failures and debris avalanches throughout its history. Large landslides can themselves trigger explosive eruptions by suddenly reducing pressure on shallow magma systems. This process played a critical role at Mount St. Helens in 1980, where the north flank collapse uncorked the volcano. Although Glacier Peak has been relatively quiet in recorded human history, geological quiet does not imply extinction. Cascade volcanoes often experience long repose intervals between major eruptions. Magma systems may remain active deep underground even when surface activity appears minimal. Earthquake swarms, ground deformation, gas emissions, and thermal anomalies are among the indicators scientists monitor for unrest. Modern monitoring techniques provide insight into the internal state of volcanoes like Glacier Peak. Seismometers detect brittle rock fracture and magma movement. GPS networks measure subtle ground deformation caused by pressurization or magma intrusion. Satellite radar can identify millimeter-scale surface changes across volcanic regions. Gas measurements reveal variations in sulfur dioxide and carbon dioxide emissions associated with magma degassing. Despite these technologies, forecasting explosive eruptions remains extremely difficult because volcanic systems are non-linear and highly complex. Not every magma intrusion leads to eruption. Some intrusions cool underground without reaching the surface. Others trigger small eruptions rather than catastrophic events. The challenge lies in distinguishing temporary unrest from escalation toward major explosive activity. Glacier Peak's geological record nevertheless demonstrates that the volcano possesses the ingredients necessary for very large explosive eruptions: silica-rich viscous magma, volatile accumulation, long-term crustal storage, glacial interaction, unstable edifice structure, and an active subduction-driven magmatic source. One of the most fascinating aspects of Glacier Peak is how it reflects the balance between constructive and destructive geological forces. Subduction continuously generates magma that builds volcanic mountains, but explosive eruptions, landslides, glacial erosion, and river incisions simultaneously tear those mountains apart. The landscape surrounding Glacier Peak is therefore not merely scenery, it is the preserved evidence of repeated cycles of creation and destruction operating over thousands of years. Valleys carved by glaciers later became pathways for lahars and pyroclastic flows. Ash deposited across distant regions became incorporated into soils and lake sediments. Rivers redistributed volcanic debris across floodplains. Even today, the volcano's shape reflects the combined influence of magmatism, tectonics, ice, water, and gravity. The enormous eruptions of Glacier Peak also highlight the variability within the Cascade Arc itself. Not all Cascade volcanoes behave identically. Some erupt more frequently with smaller events. Others remain dormant for centuries before generating large explosive episodes. Differences in magma composition, crustal structure, storage conditions, and tectonic setting all influence eruptive behavior. In Glacier Peak's case, the volcano appears particularly efficient at producing evolved acidic magma capable of explosive fragmentation. Its eruptive products reveal repeated cycles of magma differentiation and volatile buildup consistent with large Plinian systems. This makes the volcano especially important for understanding volcanic hazards in the Pacific Northwest. Even the ash deposits from Glacier Peak's ancient eruptions continue to shape scientific research today. Tephrochronology, the study of volcanic ash layers, allows scientists to synchronize geological and climatic records across wide regions. Because volcanic ash spreads rapidly and settles over large areas, distinct tephra layers provide time markers preserved in sediments. Glacier Peak ash has therefore become an important tool for reconstructing environmental changes following the last ice age. The volcano also serves as a reminder that volcanic risk is not always proportional to public visibility. Mount St. Helens became globally recognized after 1980 because the eruption occurred in modern times with extensive media coverage. But many prehistoric eruptions in North America were substantially larger. Glacier Peak belongs to that category of underestimated volcanic systems whose geological history reveals extraordinary eruptive capability. Deep beneath the forests and glaciers of northern Washington, the tectonic engine of the Cascades continues operating exactly as it has for millions of years. Oceanic crust still sinks beneath the continent. Water still enters the mantle wedge. Magma still forms, evolves, and rises through the crust. The processes that once drove Glacier Peak's massive explosive eruptions have not disappeared. They are fundamental consequences of plate tectonics and crustal magmatism. And that may be the most unsettling reality of all. Glacier Peak's greatest eruptions are not legends or myths. They are preserved physically in ash layers, pumice fields, buried valleys, and volcanic sediments spread across western North America. The mountain's quiet appearance today hides a geological system that has already demonstrated its ability to produce eruptions vastly larger than the catastrophe that made Mount St. Helens famous. Beneath the ice, beneath the fractured volcanic rock, beneath the wilderness silence of the North Cascades, the same mechanisms remain embedded within the Earth itself, slowly building pressure and darkness over spans of time far longer than human memory.